Hello, welcome back. Today we're going to continue our study of using the computer to interact with real data and be real scientists. We'll talk about least square data fitting. It may not sound that interesting, but actually it's a very interesting topic, and it's probably something you've wondered about in many of your courses, which is how does you really do science? How do you match experiment and theory together? How do you prove that a theory is correct or good or valid from experimental data? And this is an art. It's lots of science and mathematics behind it, but knowing how to do this well is not easy. It corresponds to the field of statistics, which is a combination of math and science, and we hope you've all taken a class in statistics. In my experience, many of you have not, so we'll talk about some of the stuff you need here, and let's hope that it encourages you to read some of the references to learn a bit more about statistics. We've already seen some data fitting when we spoke about interpolation, when we spoke about how to fit curve between points in a table, either polynomial, straight line, whatever, in order to get values from within the table. That's data fitting, but now we want to do a little more serious work. We'd like to talk about least squared fitting, where we actually try to prove as best we can whether a theory is good or not, how to get the best fit to data. Interestingly enough, what you'll find out is some of the topics we've used already some of the topics we've studied already can be used here. We've learned how to do searching, we've learned how to use matrices, and now we'll apply both of those to this problem as well. So let's get on with it. Take a look, please, at slide number 2. What you'll see on slide number 2 are the actual data we want to fit. So over here, this yellow graph is the data, a set of data, and it's the actual experiment done at some big national laboratory and accelerator where they measured the number of decays here in some time as a function of time for pi mesons decaying. So what they call the number here, n, is actually delta n. It's the number of pi meson decays, and they measure it at times. And one of the things that happens in real experiments is you don't measure it at every time. That would take an infinite number of times. You measure it in bins. You measure it in little bits of times. So what we have here is that the times are measured in bins, delta t, of 10 nanoseconds. And you can see that when you look at the data, because the data are not continuous, but they're in a histogram shape, and they're in bins. Okay? So that's the actual data we'd like to fit. And the theory you see here is, we did it, we got a very good agreement, it looks like. This is the theoretical curve in dash, and that's your problem. How do you fit a curve like that to these data? So that's what you'll work on. As part of that, once you do the fit, what you'll deduce is a lifetime for the particle that's decaying, the pi meson, and you can compare the lifetime you deduce to the experimental value, which is about 3 times 10 to the minus 8 seconds. So these are short times, but that's why the time intervals are nanoseconds as well, but the measurements can be done. Okay. Well, what about the theory here? You've already seen some of that theory when we studied Monte Carlo work. If you haven't, you will. And the theory is the theory of random decays, spontaneous emission. And it's a stochastic process, and that's doubly important here. Stochastic means, recall, that there's an element of chance involved. So here we have an element of chance involved in the experiment. The measurements, whether it decays or not, has some chance in it. In addition, the measurements have noise, some random fluctuations. What we know is that there's a separate theory of spontaneous decay based on small numbers. But if we take the limit of the time intervals becoming very, very small and the number of particles decaying, assuming they're very large, then for that approximation we get a model here, and the model is that of exponential decay. So equation 1 says that if the time intervals were infinitesimally small, if the total number was large, the number decaying was relatively small, then we should have just an exponential decay right there, exponential, for this curve. So this curve should be exponential decay. So the problem is, how do you fit that kind of an equation to the data? So here, let's take a look at slide number 3. We have the data again, and that's what we'd like to fit. Okay? So when we look at these data, we now have a question in our mind, which is, what does it mean to have a good fit to the data? Ooh, well, as I said, statistics is a big subject. What we mean by a good fit here has to involve quite a bit of judgment. Has to be a fit of our model. And our model is going to be a smooth curve, for example, and yet we know the data has bumps in it. So we have to be good scientists and say, well, we're speaking of fitting the data only in this case in some average sense. Okay? And that's the model we're using. It's not the exact theory. The exact theory we've done already. It's small numbers and it's a spontaneous process, but we're trying to fit a simple model. Okay? Now, so when we generally talk about fitting theory to data, there's 3 points to remember. We should write them down here, number them 1, 2, 3. If there's errors in the data, or errors could be real errors, systematic errors where you maybe hold your hand over the detector by mistake, or they could be random errors, just fluctuations that occur. So when we speak of errors, we usually mean random errors, random noise. They're not necessarily mistakes, they're noise. But if that's true, then you don't want the theory to pass through all the data. So here's a good case in point. If the theory were exactly smooth, and the data measurement obviously has noise in it, then we can't pass through all of it. We shouldn't expect it to. If we do, we've done something wrong. Okay? If the theory's wrong, then you don't expect to go through the data. Even though we can perform a best possible fit to the data with one theory, it may not go through the data. That's not a bad thing. That means it's not the right theory, which is what we'd like to find out. The third point is to actually fit most data, there's no equations to solve directly. You have to do it by trial and error searching. It's a complicated process. And we'll find some examples of that. So just in case you fall asleep by the end of these lectures, I'll tell you now, if you go to the very end, you'll see some examples where you actually have to do some searching. Okay? But we'll keep things simple here and give you some easy cases where you don't have to, just so you learn the words. Okay, so let's go back again. This is our data. That's the theory we'd like to fit. What do we do? Well, the first thing we do is we have to have some mathematical formulation, some framework, some common language we'll use to describe how to do fits. So equation 1 here is an equation, it's a derivative, the rate of decay of the particles, the ndt, the initial rate is right there, and then there's a parameter, tau, the lifetime of the pi meson in this case, in the theory. Okay? So in a general sense, we'll say that we'll describe any theory. So we say the ordinate, the value of y, is given by some function g of the abscissa x. Okay? So, and that's how we describe the data. Y is obviously the dependent variable. X is obviously the independent, because we can measure here any time we want and look at what the value of y, or the number, is. Okay? We say this function g of x must have some parameters in it in addition. Okay, so we write that down by saying g of x is a function, but it has here a1, a2, a sub m, in general a whole vector, we call it a, and a are parameters. And what's a parameter? Well, they're not part of something you measure in the data, they're part of the theory. They could be, well, they don't have to say could be, right here, equation 1. The lifetime is a parameter, it's in the theory. The initial decay rate, dn of 0 by dt, that's also a parameter. So these are numbers that appear in the theory. Okay? So when we do a fit to the data, what we're actually doing is we're not changing the theory, we're seeing if there's some parameters in the theory which we can adjust to fit the data best. So let's see how we do that. So let's look now at slide 4. Just like slide 3. Starts off, here's the data we're trying to fit, that's the theory we'd want to fit. How do we go about that? Well, first of all, we have to say we have data. We're assuming, which may be wrong, but we'll say that's our assumption, that there's some function that can fit the data. Fine. Now we'll say we have, how many data points do we have? We have n sub d data values to fit. Now D is a reminder that these are the data, and the data have the form x values, y values, I equals 1 to number of data points, plus we've added something new here. We say that there is some error associated, some uncertainty with each point called sigma sub I. And that's, that's something the experimentalist has to tell us. We can't make it up, although you can guess it pretty well by the fluctuation. That's something the experimentalist tells us. So these are the data. Okay? Each datum, each point is an x value or y value and an error. X is the dependent variable, as we've said. Y is the independent. For our particular problem, the independent variable is the time. You can just measure that whenever you want. The dependent variable is the number, or delta n, the number that decay in each interval. Okay, fine. How do we now fit data? Well, the whole trick, the whole idea of fitting data is to say, well, let's have some analytic measure of what we mean by a good fit. And someone, I wish I knew who, said, well, let's just define some variable. We call it chi-squared, right there. And this is called chi-squared fitting for this reason. And let's just say, well, let's look at how different is the data we measure, y sub I, from the theory, t, theoretical value given by the function for each point. Let's take the difference and square it. And then, because each data point can have some error associated with it, we divide by the error. And then we say, okay, we square it so they can't cancel out. It's always in the square. And if we look at it, we say, ooh, so if the theory, G, is close to the data, that'll give us a small value of chi. Very good. If the theory is very far from the data, chi-squared gets larger. So the smaller chi-squared is a better fit. The smallest chi-squared we can make by adjusting parameters in the theory is the best fit we can make. Okay. What about this factor, 1 over sigma here in the data? Well, if you look at it, for each time we square it, there's 1 over sigma squared. And that's called a weighting factor. And it says, well, let's not weight all the data points equally. What if some data point where we're really sloppy measuring, say, and has a large error associated with it? Well, we don't want to throw it out, even though people probably do. You don't want to throw it out offhand. You want to say, let's include it, but let's not include it with as much weight. So we included 1 over sigma squared as the weighting. So if the error, the uncertainty in the measurement is large, then its contribution to the chi-squared sum will be smaller. Very clever. So this is a good measurement. Okay. This is called the square, least squared fitting, as we say down here, right there. Least squared fitting means that we try to adjust the parameters A to get the least square, the least value of chi-squared. That's how we determine the parameters of the theory. How small should chi-squared be? Well, that's always a good question. The novice would say, if I was really clean, worked very hard, kept my apparatus sparkling and polished up, and only used the best theory available, I should get chi-squared equal to 0. I should go through every data point. Well, the answer is to that query, the explanation is no. If you're getting chi-squared equals 0, that means there's no error in your measurements. Okay, you've gone through every data, and if you expect some stochastic, some random fluctuations, something's wrong. Either you've made your error bars much too big, or you've put too many parameters in the theory. Okay? And so the backroom joke is, given enough parameters, you can fit an elephant. Okay, so if you go through every data point, sometimes you over-determine the fit. You have too many parameters. It's not a good theory. So what you expect is you expect chi-squared to be roughly the number of degrees of freedom you have. Okay, so the number of degrees of freedom is the number of data points minus the number of parameters. Ooh, which is already interesting. So if you have 2 data points and 3 parameters, chi-squared's negative. That means you've over-determined the problem. If you're getting chi-squared is 0, that's meaning you're fitting 2 data points with 2 parameters. Anybody could do that. That's no good. you want to fit, say, 100 data points with 2 parameters, then you've got a good fit, and then you have a chi-squared of about 98 would be a good fit to the data. So that's the key here. You don't want chi-squared to be 0. You want it to be small, roughly equal to the number of data points. Okay, so now let's move on. Slide 6. And I'm repeating these again and again because we use them again and again. Equation 1. That's our value of chi-squared. We sum over all the data points measured. We take the difference from the experimental measurement and the theory, divide by the uncertainty in the measurement, and square it. How do we make that a minimum? How do we get a best fit? Well, the answer is obvious. We want chi-squared to be a minimum. Elementary calculus, remember calculus, tells us that the derivative of chi-squared with respect to each parameter should be 0. That gives us an extremum. It may be a minimum. That's something we have to check, that it's not a maximum. So that says that for each value of the parameter, for m equals 1 to mp, so for mp parameter values, we have an equation. So we get a whole bunch of equations. So if we actually say, here's the value of chi-squared in equation 1, let's now take the derivative of chi-squared with respect to a. In equation 1, what do we get? We get 2 comes down, but it falls away because it's going to be 0. We get the first term, which is just from the derivative here. Then we get the derivative of the term in brackets, which is just dg by dA. So g is the function, the theory. We're trying to fit. A is the parameter. And the minus sign doesn't matter because it's 0. So this is the equation. So equation 3 here, of which there's a separate equation for each parameter, are the equations we have to solve. Okay, so what does that mean? That means that in general we have m sub p, where m sub p is the number of parameters, simultaneous equations to solve. There's no reason, unless you have very simple forms of the theory, for these equations to be linear in the parameters. So in general we have a whole bunch of nonlinear equations to solve. That's why the computer is great for this. That's why the search techniques we've learned about are useful. This is what they're used for, one of the cases. The equations have to be worked out for each particular theory that you deal with. So we'll work out a couple, maybe 3 simple cases here, and then we'll show you how to do it. We'll let you do it for general. In any case, you need to check 2 things. First, you have to check chi-squared's a minimum. Remember, the equations just tell you it's an extremum. You don't want it to be a maximum. That's easy to do. Second of all, you want it to be a global minimum. What are we doing here? Well, if we're going to solve all of these equations 3 for lots of parameters, we're going to do a search in an m sub p, which may be 5 or 6, multi-dimensional parameter space. There could be many minimums, and we'll just do local searches. You may need to move around, make sure that it's a global minimum. Okay, so that's no matter where you start off in that parameter space, you can't do better than that minimum value you find. Okay, so you change the minimum values, you change the starting values, and then you always look for the minimum of the minimum values to make sure it's global. You can't make sure it's global, but at least you know it's not just local. Okay, so let's take a break now. Let's look at equation 4 on slide 7. Let's do a very simple case. Let's fit a linear equation. Equation 4 is a straight line, and let's do that and fit it to the data. Okay. If you look at equation 4, it's the equation of a straight line. So it's linear in 2 senses of the word. Okay, and that's what's interesting. It's linear because there's only the first power of x and no power here. Fine. We don't care about that as far as fitting goes. What makes this linear is that each of the parameters here in little boxes, okay, are also occurring just to the first power. So it's linear in the parameters, and that's what makes it a linear search. So here's our fitted function. It's linear in the parameters. It's also a straight line. But it's really being linear in the parameters that make this so easy. So this is very easy. It's so easy that people, particularly in the liberal arts and social sciences, will call this a linear regression, meaning it's a straight line fit. We say it's just a straight line fit. Okay? So we have 2 parameters. Equation 4. We have the slope, a sub 2, and we have the y-intercept a sub 1, which we want to fit to data. Okay. Obviously, if you want to fit to data, you have to have at least 2 data points, preferably more, to get a good solution and to get a unique solution. The rule of thumb still holds. Mathematics is still valid. You need to have more data than unknowns if you're going to get meaningful solutions to the equations. Okay, so for our case here, we have 2 parameters. So if we take the derivative, which is what's involved, recall on the previous transparency, if not, go back and look. You just push the buttons. Go back, look. We take the derivative of this function, equation 4, with respect to a1, we get 1. Derivative of function g, equation 4, with respect to a2, we get x sub I for each data point. That's all we need. That's the hard part. We now put it in the equations and solve for the minimum chi-squared. So that's on slide 8, that's the equation again. We know the values from the previous slide. This is what the equations look like. Look at equations 7, 8, and 9. There's a lot of algebra involved. And I'm saving you, well, really me, the problems and the headache of actually looking at these equations and solving them in front of you. You can work them out on your own. They're very simple. They're just written here in equations 7, 8, and 9 in a very standard form. But what do we have? We have this is the closed form solution. In other words, for this linear case, we could just solve the equations. Here's a value of a1, and here's the value of a2. And it should just involve data points. That's how you look at these equations. Does it? Well, we're dividing by this delta, which is defined down here. We have these s's. What are they? Well, let's look here. S, which occurs someplace in here. There's S right there. S is the sum of all the data points of 1 over the error squared. Fine. S sub x occurs right here. S sub x, you sum over all the x values. In this case, it would be like the time divided by the error squared, all the data points. S sub y, we just sum over the y values. Then we have a double index here, xy. Here's a double index. And then you're just summing over the product of the x values, the y values. These are the measured values divided by the error squared. Good. And delta is just this combination which occurs. So this is just handy form to compute. But to repeat, we're fitting a straight line. You measure as many data points as you want. ND can be anything. You just do these sums. And then we get a curve. What else do we get? Well, we get from statistics, which is very handy, we get what's called the variance. So not only do we deduce in equation 7 here the values of A1 and A2, we can deduce at least some kind of a measure or a metric for how good these values are. So you hear statisticians talking of what's the certainty, blah, 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 in these equations. Well, what we can say here is the variance, the expected uncertainty in A1 is given, called sigma squared. The variance, the square root of that, is often used as well. The variance, sigma squared, is just this number sxx, which we calculate over here, divided by delta. The variance in A2, the uncertainty, is also given by a similar equation. So we predict not only the values from the data, but the uncertainty in the data. Okay. So now it's a good time for a break. We're going to apply this. You've seen a lot. Stop, go back, make sure you know what the equations mean, and then we'll start applying them. Are you refreshed now? You ready to go? I hope I am. Okay, so let's go ahead. Let's look now at the next slide, slide 10. Here's our problem again, okay? That's what we have to do. Here are the data. We want to fit an exponential, equation 1, to these data, and by doing that, deduce the best values for the lifetime tau, and then what the initial decay rate was. The lifetime is something everybody cares about. The initial decay rate, people don't care about it so much, but they have to both come out, and then we want to judge how good a fit it is. So that's your problem, okay? That's what you could work on. If you're smart enough, if you think you're good enough, just turn me off now and go ahead and do it on your own. If not, I'll show you how to do it. Well, let's look at equation 1. We know how to fit a straight line. Equation 1 is not really a straight line. It's an exponential. So what we'll do is we'll say, let's be a little clever and let's try to fit equation 1 to the data by taking logarithms. Okay? Aha. So we start off first by saying, how do we implement the fit? Well, we implement the fit first by constructing a table. So you do this on the computer. You want to read all the data values, delta n and delta t, from the curve here. And you can say, well, why don't you give me the data? Well, because this is all we have. This is what's published in the journals, so that's not so bad. And then you can estimate the errors, since we're not given by the experimentalist, by I. So let's look at that for a second. We know what the times are here. They're bins. Okay? So we can say, okay, let's call the time as the value in the middle of a bin. That's easy enough. So that would correspond to right there in the middle. So we read that from the graph. We could just say, oh yeah, that's, it's 2, 4, no, it's 10. Fine. So that's going to be 85. That's the time. Easy enough. Then for the values of n, we have to read off the graph. So you read it off as best you can. And then you could say, well, what's the error? Well, obviously there's a lot of error up here because there's a big fluctuation, and there's smaller error at the bottom. So you could say the error is roughly the difference we're seeing here from the smooth curve. Your smooth curve, you can imagine one in your eye, or you can use one of the rules for large numbers. If we had large numbers, we'd expect the fluctuation to be like the square root of n. So if that could work here too. If n here is 30, square root of n might be 5.5. If n here is only 10, the square root might only be 3. That's a reasonable error. So that's the data. Okay? And then, as I said, what we really want to do is not fit those data directly. We'll make a semi-log plot. So either you can imagine making a semi-log plot, or you just take the logarithms of the decay rate measured each time. Don't be confused. It says number here. That's what the experimentalists measure, but it's the number of decays, delta n, if you want, in some time interval, which is always constant. So it's actually a rate. And we expect that rate, if we take the log of equation 1, the rate will be linear here in the parameter 1 over tau. So we can deduce 1 over tau, and consequently tau, and it's also going to be linear in the logarithm of the initial decay rate. Okay, so those are our two parameters in the theory. We get them out. So this is the equation of a straight line. X is now delta t, a is minus 1 over tau, and b is that logarithm. Okay? So when you're done, make your best fit, a linear curve like this, and then plot the two on the same graph to see how good it is. You always have to plot. If it looks bad to your eye, it's going to be a bad fit, regardless of what the math says. And that's what we've done here. This is actually a curve to the data. Okay, so go home. If you want, you can quit right now, work on that. Or you could say, well, I'm better than that. I'll move ahead. Can we do something more complicated? So look now at slide number 11. Okay, so in the previous exercise, we did a linear fit to a straight line. Linear being in the parameters. Now at least the words won't make so much nonsense to you. Now let's do a linear fit to a quadratic function. In other words, we have equation 1 here. We have a parabola. It's quadratic because there's an x and there's an x squared. So that's where we say quadratic. But it's linear because the parameters a1, a2, a3 only occur to the first power. So the equations are just like we did before. If we take the derivatives, we just get, with respect to a1, we just get 1. With respect to a2, we get x. With respect to a3, we get x squared. We can take those derivatives. They're nice, simple functions. Okay, so it's very easy, and there's no a's that appear in the derivatives, so we get simple equations. What would a nonlinear fit be like? Well, let's say if we wanted to fit the function, as I show here, that has an exponential, a in the exponent. Well, that would be nonlinear because a is now not linear. This function's not linear in a, but rather it's exponential in a. Okay, so that would be an example. I won't work out the details here. I can. In fact, I worked them out and I put them in the text, and you can look at them and some more. But if we have this simple function in equation 1, the chi-squared equations tell us that we just take the derivative of chi-squared with respect to each parameter. We want that to be 0, so we have a minimum. There are the 3 zeros. We take now the sum of all the data points, each derivative multiplied by the function. We know what the derivatives are right there. We get a bunch of equations to solve. They are linear equations, simultaneous linear equations. And on the next slide, 12, take a look at, there are the 3 equations and 3 unknowns. So let's look at it for a second. How do you look at it? Well, you look at it to say, this is what we want to fit. What are the unknowns? And what are the equations? Well, remember, when you do fitting, the unknowns are not the y values or the x values, they're the parameter values. So here A1 appears in each equation, A2 appears in each equation, and A3 appears in each equation. The right-hand side has just numbers, okay? So these S's are essentially the same S's we had for the linear fit. Now there's one of them here with 3 indices. That just means you take 3 data values multiplied together. Okay, so it's the same idea as before. And we have 3 equations, 3 unknowns, 3 linear equations. We can use a matrix to solve them. For a simple problem like this, you can do it by hand, but it's nice to see if the tools work. And if you had a higher degree polynomial, 10th degree, say, you'd have 10 parameters, it could still be linear in the parameters. You'd want a matrix to fit it. So we work it out in the book a little bit more, and we say, we can just write equations 2 to 4 as a matrix equation. That's just alpha, which is a matrix of known values, so there's alpha, all these S's which are known, A, so this is the unknown, A, that's what we have to solve for, and beta is, again, the S values, the right-hand side, that's known. So we can solve this set of equations just using our late matrix library routines. And I'm a nice guy, okay? So if you recall, when we looked at the JAMA matrix library, we did a sample problem. It's called JAMA-fit.java. That was the problem to solve. Or actually solved the previous linear equations for you as an example of matrix fitting, and here we can do it as well. So this is a very good exercise. Okay, so what about a real case? The last slide now, we're nearly done. This is a challenge problem. For those of you who think, or maybe you've had courses or in this stuff, and you think the stuff we've been talking about is just too easy, is just too pedestrian, here's a real physics problem, okay? So here now are the data of some cross-section, sigma, as a function of energy. Hey, you may recognize this. These are just the data values we interpolated on in the past. So here's the table of values I gave you before. And we're saying, here's the table of numbers, here are the numbers, and we'd like you to make a best fit through the numbers. Ooh, okay, so, I could say, well, if I was doing this by hand, I'd say I would just draw a nice smooth curve, show my fantastic artistic ability, and I'd get a fit like that. But if you had, well, physicists just say, can't be right. For example, you can't have a peak, a cusp. Nature doesn't have cusps. And also, there's obviously noise in these data. You wouldn't expect to go through the data. So here's the function we want you to fit to the data. It's called a Bright-Wigner, named in honor of 2 Nobel laureate physicists, Bright and Wigner, who did this in their spare time, I think. But you see, it's a function. E is the parameter, energy, and F is just the value of sigma, the cross-section. Okay, or what we called sigma before. And then there's parameter here. There's one parameter, F of R, just the height. Another parameter is E sub R. That's the, E sub R is the position here where the peak occurs. So that will tell you what E sub R is. And the third parameter is gamma. Gamma here is the full width at half maxima of that curve. So that's, the value of gamma will give you that. So here's a function, fit it to the data, deduce the resonance energy. It should be something about 75. Here, deduce the gamma, the full width at half maxima, and it should be something about 20, 30, whatever that looks like, and try it. This is not easy because the equations you get will be nonlinear, and you can't solve them with just linear routines. You have to use the Newton-Raphson search method. Okay, so this is a challenge problem. It's worthy of graduate level. So we're done. Go to the lab, try out the simplest problem or the more complicated one, whichever your instructors told you to do, and then we'll come back and move ahead. Bye-bye for today.